Okay, anyway, let's kick it off a little bit late. Sorry for the delay, everyone. It's our pleasure to have Lydia Liu here from Berkeley, and she's going to present her work on delayed impact of fair machine learning. This work won the Best Paper Award at ICML recently, and it blew us away when we saw it at the conference, so we thought it would be a good idea to bring her here and have her tell all of you about it as well. So thank you very much, and take it away.
Okay. Thank you, Ofer, for the kind introduction. So I'm going to talk about joint work with Sarah Dean Esteroff and Maxim Kowitz, who are my colleagues at Berkeley, and my advisor, Moritz Hart. So maybe many of you in the audience here have seen this cartoon, which kind of documents the very brief history of fairness research in machine learning. And the trend here is like an increasing trend in the number of papers. Right, so when I make these slides, the joke here was that, I can forecast that in 2018 it looks something like this. But now that we're at the end of 2018, I think this is like a realized forecast. There's been really, really a lot of interesting work done about fairness in machine learning. So if I were to talk about the field at a very high level, I'll make the following observations. First is that there have been many mathematical quantitative definitions of fairness that people have proposed. And so earlier this year, Arvind Narayanan gave a tutorial that listed at least 21 different definitions of fairness. And I think now it's probably more than 21 different definitions. And so the good news is that many of these fairness criteria that people have proposed and have written down can be achieved individually by efficient algorithms. So if I said I wanted to achieve, say, demographic parity, I can pick one of the many ways that people have tried that worked. And there are many different categories I can put these algorithms into, which is probably not going to do justice to the whole literature, but there's post-processing. You can reduce it to black box machine learning, which we already know how to do. You can also try agnostic learning, and recently we find that some fairness criteria, we can get guarantees on that just by doing unconstrained machine learning. So empirical risk minimization without any added ingredients also gives us some notion of fairness. So that's sort of the good news. And then the bad news that many of you might have also heard of is that there have been a bunch of impossibility results about fairness criteria, which is if I achieve a certain fairness criteria, I am doomed to not be able to achieve some other fairness criteria. So there's no way to and with 21 different definitions, you can imagine there is no way we're going to be able to achieve all or even like many of them. So that is sort of like the story. And so if you are a practitioner, or if you are thinking about like how do I make the algorithm that I'm implementing like fair, then I might want to think about how I should prioritize the different fairness criteria, or how do I want to evaluate these zoo of fairness criteria for my particular application. So one way to think about evaluation is to look at downstream impact of your algorithm and of your fair algorithm. And this is what we call delayed impact in this paper. So if we step back a little, in fairness literature, there is this thing we call the protected group, which is a group of individuals that's defined on a basis of what we call a sensitive attribute. So this could be a race group or a gender group or some other group that we care about. And when these papers propose a certain fairness criteria, there's an implicit assumption that by applying a fairness criteria, the protected group would be better off. Or at least by applying a fairness criteria, we kind of protect them from a harm that would not have occurred otherwise. So in this work, we want to critically examine whether this implication is true, that we really, with this fairness criteria, protect these protected groups from some notion of harm. So let's start by looking at a simple example. So this is our favorite example of like the credit scoring setting. So where we're trying to decide who to give loans to based on their credit scores. So here I'm showing you two groups with two different histograms of their credit scores, right? So there's the blue group and the orange group, and each group has slightly different distribution of scores. And here with higher scores, there's a higher probability of repayment. So here, this probability of repayment is indicated by sort of the solid versus the empty circles. So the solid circles indicate the people who would actually repay, and the empty circles indicate the proportion of people who would not. Yes?
Is there an assumption that these are calibrated predictions, or possibly they're already bias built into the blue and red
In the
blue and orange
scoring,
probabilities?
in the scoring. Yeah, so we actually allow for that. I will make this more formal later on, but yeah, the short answer is that we just assume that the scores are monotonic in the true probability, so they are calibrated in that sense. But there are also like other, yeah, that's definitely a consideration. Yeah. Yes. Any questions? Yeah, yes.
I just wanted to verify, is it an artifact, is it intended or unintended that in the bottom blue row the proportion is lower for not repayment, even though the score is lower than the row above? For the blue dots in your graphic.
Oh yeah, it looks like the probability of repayment is different for the same score for different groups. You're saying, or
No. Like, for the blue group in particular, if I look at the bottommost row and the middle row, the bottommost row looks like fewer people don't repay. So actually, it should have a higher score, or maybe that's just.
Oh, so the scores are increasing this way. So the scores are the x-axis.
Okay,
Yeah.
sorry.
Yeah. So it's a usual histogram.
Okay.
Yeah. So.
Can groups have non-zero, non-empty intersection?
Yeah. Maybe I will go on first and see if your questions get answered later on, because I'm just giving a non-rigorous example to sort of kick things off. Yeah. So basically, we have so the empty circles indicate the people who would not repay. But as the bank, they do not know who are these people. They just know at each score that is a certain proportion of people who would not repay, right? So just with these scores, now the bank wants to know, like, how do I give out loans? If I also care about some notion of protected group, and I want to make sure whatever I'm doing is fair in some way to the protected group. So let's just pick one of the fairness criteria that we saw just now. That's called demographic parity, and that means that for each group I must approve the same fraction of loans. So if in the orange group I'm giving out 60% of the people giving them loans, then I must do also 60% for the blue group. So this gives rise to two different, possibly different threshold scores in each group, and I give loans to people who are above that threshold. Yeah. And then now I do this and I decide to give out the loans, and so people will either default or repay on the loans that they get. So for people who did not get any loans, then their scores don't change, right? Because we just assume that you can argue about whether that is true or not. But let's say they don't change if they don't get any loans. And those people who got loans, if they repay, their scores eventually, their scores move up in the next time step. And the people who got loans but they defaulted, their scores move down. So we can also talk about what's happening at a group level. So at the group level, the orange group, everyone happened to repay their loans and the scores got better on average. And then with the blue group, more people defaulted than they repaid, so the scores got worse on average. And I can argue that this is a concrete way to characterize harm, because if you have worse credit scores on average, you're more in debt on average, and you also have less access to credit in the future. Right, so what has happened in this example is that I've shown you something that might be slightly counterintuitive, which is that once we applied a fairness criteria and we looked at the downstream impact that the loans have on the scores in the next time step, it didn't seem to help the protected group. In fact, the protected group experienced more harm on average. So this really motivates us to study what is more systematically the delayed impact of these machine learning or classification decisions. So in our work, just to summarize, we do sort of the analysis, but at a systematic level using this tool called the outcome curve that we introduced for comparing delayed impact of different fairness criteria. And using this curve, this tool, we can provide complete characterization of the delayed impact of 3 different fairness criteria, which includes demographic parity, which I mentioned just now, And then finally, the key observation is that without modeling the impact a priori, we do not know what the fairness criteria will do. So in particular, applying fairness constraints may cause more harm to the group that they intended to protect than not doing anything at all. So I'll maybe introduce the problem setting a bit more formally. So the score that we have already seen just now is a scalar random variable that's a function of an individual's features. And we can just think of this score as coming out from a black box machine learning algorithm. So for example, this credit score we have here is such a score. And an individual has one score, and any group of individuals has a particular distribution over scores, right? And which is the same thing as the histograms I showed just now in that example. And the main assumption that we would like to make, which is also something that is very reasonable to think about, is that the scores actually correspond to the individual success probability. So formally, we want to say that this is a monotonicity assumption, which means when you have higher scores, you're more likely to repay. Yeah. And yes.
If you assume that in fact there was a bias in the construction of the scores, that the blue group, the scores actually mean different things in different groups. So then the fairness criteria could be trying to compensate or correct for that.
Exactly. So we also consider this regime as well, and then you do get some you get different behavior under that regime as well when you have but I'll get to that. Thanks. So with these scores, the institution wants to classify the individuals using these scores, and it does that by choosing an acceptance threshold score. So the threshold score is chosen to maximize the bank's utility, right, or the institution's utility. And in this case, it's the expected profit that they're making from all the loans that they have approved. It's like the sum of the rewards minus the sum of the losses, right? And we're taking expectation because each repayment versus default is a random event for the individual. So now, if we decide on a certain threshold score T, for this particular group distribution, that corresponds to an acceptance rate beta, right? So I'm saying that there's this one-to-one mapping, if you will, between the threshold score T for a group and the fraction of people I'm accepting from this group. Right, so I'll just talk about these two things kind of interchangeably. So the decision variable we have for any group is their threshold, and also equivalently, the decision variable I can say is the acceptance rate in that group. So when there are multiple groups, just a reminder that the thresholds don't have to be the same. And in fact, if you're applying a certain fairness criteria, it becomes necessary for you to enforce group-dependent thresholds. So we just allow for that. And then now we're ready to define what we mean by delayed impact. So the scores of the accepted individuals, they'll change depending on the success. So it will increase if they repaid their loans. It will decrease if they defaulted on their loans. So then at the group level, the group's distribution over credit scores will also change. So we want to summarize this change by looking at the average change in score. So we call that quantity the delayed impact. It's just denoted here as delta mu, but that's the quantity we're interested in to characterize like whether a group is benefiting or experiencing harm. So if the first result here is the outcome curve, which is under very mild assumptions, basically the monotonicity assumption that I talked about just now, the delayed impact is a concave function in the acceptance rate, right? So if like just plot out the delta mu function as a function of the acceptance rate, it looks something like this. And what's happening on the x-axis, that's where the bank is making its decision, right? It's the bank's decision space for that group. And if we have an acceptance rate of 1, that means the bank is giving out loans to everybody, right? Everyone gets a loan. And acceptance rate of 0, that means nobody gets a loan. And then the delayed impact at that point is also 0 because the bank is not doing anything. There's no effect it can have on people's scores. So then the natural strategy for the bank is to maximize its own utility, which is its profit. So it chooses this acceptance rate of beta max util. So any policy that gives out has a lower acceptance rate than beta max util, we call that relative harm because you're having like less positive delayed impact, right, on that group, right? So that would be you basically have less positive impact than if you just maximize your own profit. And now because defaults, we model the defaults as being more costly for the bank than for the individual. So it turns out that if the bank just maximizes its own utility, it will deny loans to some people who are otherwise likely to repay. So by making the bank give out loans to more of these people and then sacrificing some of its expected profit in the process, we can actually increase the average score change further. So this puts us in this second regime called the relative improvement regime, where my average score change is more positive than under utility maximization. And I can keep increasing this delta mu until the unique maximum point of this curve, which we just call this the philanthropic optimal because that's where the delayed impact is maximized. And now if the bank were to give out even more loans, then now I have to start giving out loans to people who are less likely to repay, right? And on the average, that brings down the score of that group. So even though I'm still in the relative improvement regime, right, I'm starting to see less, in fact, negative change in the score, as a negative rate of change in the score. So then I'll get to a certain point where, again, I'm in the relative harm regime, and I'm doing worse than under utility maximization. And then finally, then the point, I reach a point where my average score change turns negative for that group. And this is somehow the egregious part of the curve where by having an acceptance rate so high that I'm giving out a lot of bad loans and I'm really pulling down the group's average score change. Yeah, so what I've done here is, introduce 3 regions of interest on this outcome curve. And now we can ask the question of if we choose a certain fairness criteria, which part of the curve am I likely to end up in? And what do different fairness criteria put me at different parts of the curve? And what can I say about that? So before I go, yes?
Just a question about beta max U2. Is that, should I think of that as a, because it's utility maximization, is that a threshold that's common across all the protected groups?
Yes, so in this particular setting it is. If I do utility maximization, I get the same threshold for all the groups. Yeah. Yes.
Is it not true that the bank, if someone was going to pay, then if they give that person a loan, they're making money off of that?
Sorry, I'm not sure I got you.
If the bank gives someone a loan and they pay back successfully, do they make money there? Or do they should make money.
Right.
So if there's a probability that's known of whether this person will pay back or not, is it not in their interest to give it to as many people as possible who will pay it? In other words, why is beta max util and beta philanthropic optimum not the same?
Right, that's exactly because the utility structure for the bank and the individual is different, or at least in this model is different. So we thought, I guess this can be debated, but we thought that it's reasonable to model defaults as being more costly for the bank than for the individual. Like for the bank, it will lose like that amount of money, whereas for the individual, your credit score might change, but it's not, the ratio is not as drastic. So here we're just talking about the relative size of the ratios of like score change under default versus.
Okay, not the chance of the loss, but how much is lost.
Yeah. Yes. So just to recap the fairness constraints, so it's an alternative to unconstrained utility maximization, which is, I guess, unconstrained machine learning. We can think of, we want to maximize utility instead subject to these constraints. And demographic parity, which we already saw, is constraining to equal acceptance rates across groups. So if I have the distribution of scores for both groups, I want to make sure I'm selecting, I want to look at all the dots here, and then I'm selecting the same fraction of dots on, for both groups. And then there's also another fairness criteria called equality of opportunity that we're going to look at. And this constrains our policy to have equal true positive rates. So slightly different, we are only looking at the solid dots, which are the people who would repay, and we want to make sure we are selecting the same fraction of solid dots across both groups, right? And so the question now is, where would the two fairness criteria put us on the outcome curve? So the first theorem is that, in fact, equal opportunity and demographic parity can put us anywhere on this outcome curve, in the sense that we can always find regimes where they are causing harm or relative improvement or improvement. So all three regimes are possible. And in contrast, if we just did unconstrained utility maximization, that never causes active harm. And this is because of that assumption I was talking about just now, that where the defaults are, we model it as being more costly for the banks than for the individuals. So this is kind of the situation we are in. We have that beta max util is always here, and it's before the maxima of this curve, so it's never going to cause active harm. Whereas we can always find some situation where the two fairness criteria can be anywhere on this curve. So then the question now is, can we say something less general than that? Like, is there any situation where we can compare the two fairness criteria? And the answer is yes. So there also exists like a large class of problems where we can say the following, which is that demographic parity is maybe causing active harm or relative harm in these settings by over-accepting. So it has a overly large acceptance rate and causes harm that way, whereas equal opportunity puts us in the relative improvement regime by being more conservative than demographic parity. And then on the other hand, there's another type of harm that equal opportunity might cause, which is by under-acceptance. So if we look at this on the outcome curve, that's basically in the regime of relative harm that's on the left side. So this is so equal opportunity can put us in this regime, whereas demographic parity just never under-accepts relative to utility maximization under all circumstances. So one possible situation is where your equal opportunity is causing you more harm than under utility maximization, whereas demographic parity is doing something that's better for your group. So this is also something that we mentioned just now, which is what if my true repayment probability is not really captured in the same way for the two groups. So we call this measurement error, and specifically we mean this particular kind of measurement error where the bank systematically underestimates the repayment ability of one group. And we can think of this as a reasonable model for misspecification of the score. So maybe the bank thinks that the credit score of 300 corresponds to 0.8 probability of repaying. And then in the orange group, this matches their true probability of repayment, right? And then for the blue group, something not so good happens, which is for someone who has a 0.8 probability of repaying the loan, you actually assign them a lower credit score. So you are underestimating their repayment probability, right? So, so this is what we call measurement error. And then in this measurement error setting, the acceptance rate for the group that's underestimated is always lower than if the bank actually knew the true mapping between scores and repayment. So scores, and probability of repayment. So this also holds for applying for like constraint optimization under fairness constraints. So we can see this on the outcome curve as follows. So if I knew the true scores, my acceptance rate under profit maximization is beta truth. And if I underestimated them, then I would have I would choose the acceptance rate beta error. So it's actually in this relative harm regime. Whereas for demographic parity, we said that it tends to over-accept. So it might be in this relative harm regime if I knew the true scores. But since I don't know the true scores and I have a measurement error, then I actually under-accept, right? So my demographic parity acceptance rate under error is actually here. So now we see that, okay, this might be a situation where utility maximization doesn't give us, also can give us like harm. And whereas like the demographic parity yields like a more favorable delay impact for the group by making up for this measurement error. Yeah, so this might be one reason why you want to consider a fairness criteria that is somehow more generous.
One question.
Yes.
When you're considering the measurement error, are you still assuming a monotonicity?
Yes.
And so the measurement error is somehow
It's like a
overlapping.
uniform error across the like.
It's monotonicity within each group, but not between, or not overall.
Monotonicity is within group only, or is it global?
Monotonicity means there exists like a monotonic function from the scores to the probabilities for every group.
Separately for every group, or also overall for the two groups? That was the question.
Overall for the two groups, but then you have to allow for different functions for the two groups, right? If you want to talk about measurement error. Yeah. Does that answer the question?
So the monotonicity is across just from scores. It's scores to probabilities. And in the measurement error, you have to be careful about not violating the monotonicity.
Yeah, so the way we introduce measurement error is like to introduce the same error at every score, just for that particular group. So I mean, then there still exists a function that is monotonic that maps scores to. Yeah, we just add the size of the error. Yeah. Yes.
So I guess at a high level, I'm wondering, like, for the kinds of, like, at least for the illustrative example you have here, and it seems part of the reason why we are getting this delayed impact in a way that we didn't maybe anticipate with our fairness constraints is because there is effectively this feedback loop that we didn't reason about. That that not the loans we give don't just go into actually like giving people loans, but they also go into feeding back into their credit scores and affecting their future credit worthiness. And I'm just wondering, like, so should I think of this partly as also a failure of trying to do supervised learning in a setting where I really should be, say, at least like thinking of more like bandits or reinforcement learning type techniques, which are actually systematically thinking about the feedback loop we have present in the data collection, or and it does, like, if I were thinking about sort of, so there is this line of work from folks at Penn about basically trying to put fairness in those types of approaches, right? So do the delayed impacts sort of go away when trying to think in that fashion, or how does it play out?
Yeah, I think in general, there are kind of two ways of looking at it. One way is like what you said, like maybe we should be looking at more the dynamic impact of machine learning, that we should consider like downstream impact when we're making decisions at the current time step. So I think that's definitely like sort of the right way to go. In this paper, in this work, we only look at one step ahead in the future, and even then we sort of see like interesting behavior. So that's one aspect. The other aspect, though, is that we are trying to sort of characterize like why fairness needs to be context sensitive. Because you can't really talk about delayed impact without having like a reasonable model of how people are affected. So under different models, like if I choose arbitrary models for delayed impact, then I can always find like some fairness criteria that is going to give me something unreasonable. So I guess the message on this side is that we shouldn't be trying to say, oh, this is the best fairness criteria, like let's apply it to everything, right? Without thinking about what my context really requires. If I have a particular outcome model that I think matters, then maybe I should prioritize that over like choosing something for, I don't know, other reasons, or choosing the same tool for all my projects. Yeah. So I've talked about the theorems, and here I will also share some simulated experimental results on these like real data. So these are credit scores from this federal government report on credit scoring. And what we did with this data is that we used this empirical data labeled by race. We just look at 2 race groups in our case, and then we estimated the group score distributions and the repayment probabilities. So we make because previously we made the assumption that there's a monotonic function from scores to repayment probabilities, so we can check whether this real data satisfies that. And it seems that, right, except for this little kink there, approximately it is monotonic, so we expect our theory to still hold reasonably well in this situation. And then what we cannot estimate from the data is the utility structure of the bank and for the individuals. So we have to choose, in particular, we have to choose the bank's profit versus loss ratio for a certain a repaid versus defaulted loan. And we also have to choose the change in credit scores when an individual defaults or repays. So we just choose these ratios so that it satisfies our assumption that the bank's profit to loss ratio is somehow more drastic. And then we can compute the outcome curves empirically and look at the delayed impact when we apply different fairness criteria. So if we just plot out the outcome curves for the two groups, we can already see, right, that first of all, the two groups have rather different outcome curves under with the repayment probabilities that we estimated and the model parameters that we chose. So in particular, the black group has this larger regime of acceptance rates where it's going to experience active harm. So if we just looked at what we would do under utility maximization, we're here in the bottom, I'm plotting the bank's expected utility function as a function of acceptance rate. And we just choose the maxima on both sides, and that's the threshold that we get, and both groups are experiencing a positive score change. If we use demographic parity, on the other hand, this enforces equal acceptance rates for both groups, right? And then now the black group is in this active harm regime. And if we choose equal opportunity, just now we predicted that equal opportunity is more conservative. And okay, now we're back in the improvement regime. So what we claim that would happen also is something that we can observe in real data under some reasonable modeling assumptions. And then here the question is, why is there a large difference in the delayed impact for the black group, right? So the issue is that the black group is a minority group. So when we change the fairness criteria that we're applying, then the black groups, if we look at the bank's utility curves for the black group, it shifts a lot more, right, when we choose different fairness criteria compared to the bank's utility curves for the white group. So this misalignment in what maximizes the bank's utility and what maximizes the group's score change is more drastic for the minority group. And that visually we can see why when we change the fairness criteria, this is disproportionately affecting the minority group. So I'll just summarize what I've told you. So we've proposed this tool called the outcome curve that offers a way to deviate from just pure utility maximization while keeping an eye toward improving outcomes, right? And like I mentioned just now, we see this as promoting the need to have more context-sensitive models of delayed impact. So we think that fairness should be considered within its particular application, and it's not like a blanket solution. And there are also many interesting questions for future work in this space. So we need to, not just for delayed impact, but for fairness in general, there's a need to move beyond binary decisions. So many of the work is based on this 0-1 prediction, but in reality, we have like richer decision spaces involving different interest rates, different loan sizes, and how do we reason about fairness in that situation. And also, we introduced the mean score as a way to summarize the delay impact. But that begs the question, is the mean score the right measurement to use? What other things should we be using to reason about the delayed impact? And then there's also been a lot of other work that similarly consider like the dynamics of the impact of machine learning algorithms, how machine learning algorithms change the distribution of some variable. So in this case, we looked at this indicator of welfare. In other papers, they look at other things like change in demographic sizes and so on and so forth. So there's definitely a lot of like exciting questions in that space, like what do we mean by feedback loops and what kind of feedback loops are present in these different models. So I definitely think there's a lot of exciting questions to be asked. Yeah, thank you guys for listening. Yeah. Yes. Hi. Yes.
So I again wanted to bring up this issue of the case when groups overlap.
Right.
So mathematically, do these results still hold up to that situation? Essentially, what I'm afraid of is there may be a large overlap between some of the groups, and maybe, I mean, just purely hypothetically, there are situations where it looks like you're improving on fairness mathematically, but it turns out that because of the large overlap between two groups, you're like making the situation much worse for people in that overlap, despite the fact that they belong to, say, a protected group.
I see. What do you mean by overlap? Are you saying like does the support for the scores, does the support for the two distributions overlap?
So people belong to several groups at the same time.
Oh, you're saying
people are
they're
black
different
and
groups.
foreigners, for instance.
Right,
or
right.
something like this.
Oh, I see. Okay, I see what you mean. So yes, so in this case, I guess whatever we are saying is assuming there's one group attribute that we care about, which is like a single group attribute. So we are only talking about like that one group attribute. But then, of course, you would like to reason about like when you have intersectional groups or like other groups that are not a priori defined. So I think that would not be the question that we were setting out to answer, but what would be the connection here? I guess, yeah, I guess it would only make the problem harder to reason about. Like, yeah, but I assume, I think even in that situation, we'll probably have similar impossibility results. So if we define an outcome model, I can, and you are doing well according to some other group, and then I can always introduce another group attribute where it will be worse. But I guess I'm not sure what is the question that you were thinking of.
The only thing I was wondering is how much these results extend in their current form, cases where groups overlap.
Right.
I mean, you answered the question.
I mean, there is like some relevant work, which, I mean, so when you have sort of these overlapping large number of groups, there is also becomes a question of how do you like detect even fairness violations, and there's been some work along those lines for like how do you effectively algorithmically search for subgroups who are getting fairness violations, but that's probably the only extent that is related.
I think at that point it's not even clear exactly what fairness means, like what these thresholds would be for people in the intersection, right? Because the thresholds in the model can be different depending on the group, and then so what do you do with people in the intersection? Thanks.
Is this that you're thinking about the one-shot decisions here? When we go to multiple decisions in a row, I think the situation even gets more complicated by the fact that the black box is going to be updated at some point, based on the feedback that people are, who pays the loans and who defaults. What are your thoughts about how these fairness criteria should be reasoned about in the long term, where models get updated and there are all kind of complex interactions between what people do and what the feedback the models see when updating.
Yeah, that's a great question. I'm actually very interested in that question. And so when we started out with this work, we had an eye towards like multiple steps, right? So we wanted to compute, what is the like multi-step delayed impact? And it turns out to be sort of, it's kind of unclear what is the right model to talk about feedback loop in that case. So I think it's still like an ongoing thought project for me as well. There have been some work that take this to the extreme, so they show results when time goes to infinity. You equilibrate and you have a certain, like if I apply a fairness criteria, I get a desirable outcome, like as time goes to infinity. But in reality, we never equilibrate. Right, so that's also the difficulty. So somehow either we have something we can say about one step, or we can only say something about the very distant future, which might be irrelevant already. So yeah, definitely that's something I have to think about more. Yeah. Thanks. Hi.
Do you have thoughts on how we can actually accurately measure? Because I mean, one of the problems, right, is the variables you don't know. So, for example, you might have two groups that are low income, but one of them primarily lives in rural areas where no one's around and experiences very different crime, right? And the other ones don't, and that leads to stress factors, it leads to loss of job, lots of other things that affect risk factors. How would you think of even doing the measurement so that we know that what we're measuring reflects reality as well in terms of the individual people?
Yeah, right. I think somehow this sampling problem is like a very big issue because, whatever I'm measuring already reflects the biases in the current system, right? Then, like if people are, I guess if I'm understanding your question correctly, for people with high default rates, it might be due to many different risk factors, and some of them might be due to like injustices, for example, that are present in society, and do we take that into account or do we like correct for that? Yeah, I think that is a very hard question. In general, like it's sort of, if I really want to solve this perfectly, I would have to do like causal inference, right? Or something that will allow me to take into account like what would have happened instead, right? If I didn't have these social structures that are pushing people down, right? What is the true repayment propensity? And I guess I don't have a good answer to that. Yeah.
Can we maybe we're already losing many people. So it is going to be around a little bit longer today. Maybe give her a little while to recover from the talk. But we're only going to leave at 6 for dinner. So if you want to grab her, this would be a good time. And then some of you have meetings with her tomorrow as well. So maybe let's thank her again and adjourn.